Hi people, welcome back to the next lesson on deflection. I'm flicking back to the notes that I spoke about earlier. There's the note there, and I worked through those steps in order how to find the deflection at various points in the beam. We took that beam over there where we had to define deflection at B and C and the slope at A, and we've done that in the last lesson. In the next lesson, if we keep going down there, there's various beams to do. I'm gonna work through example number 5. There we go. Sorry, it says example where UDL doesn't extend to the end of the beam. I will explain in a moment the significance of that note there. The question says there, find the deflection at A, C, and E. Why would we not want to find the deflection at B and D? Because the beam is bending over and D, so the deflection at B and D, the supports, is equal to 0. So if I could call up some tools there, if I could make a comment there, and if I could do that, okay, and if I could draw the beam in, the beam will be bending something like so. It will be bending like so over there, and we're doing that there like so, and we're doing that there. Okay, so there's a deflection there, okay, there's a deflection over there, and there is deflection there. Okay, so the deflection at B and D is known. Those are the boundary conditions, because we use those facts that at B and D deflection is 0, and from there we find the constants of integration C1 and C2. Right, let's do this. Okay, here we go. There's the beam. I've done the reactions already. The first thing is find the reactions. If you're given the reactions, use them as they are. If you're not given, find them out first. Okay. And if they are sitting there, don't go do it, because you're going to waste time. Right. So we take moments about the right hand end of the beam, and the left hand end of the beam is the origin, where X starts and starts at 0, 0, and by the time it gets to there, it's equal to the full length of the beam. Okay. Right, so we need to set up the moment equation, and the moment equation, so M, M at X is equal to EI d2y dx squared. There we go. M is equal to E times I times the second derivative of dy dx, where y is the deflection and x is the distance along the beam. Right. I'm going to set up my bending moment equation. I'm taking moments about E. Okay? So about E, VB and VD will be positive. Okay? So I'm going to say VB multiplied by the distance from there to there. But the distance must be given in terms of X. So it is X minus 0.6. So it's times X minus 0.6. Plus, why is it plus in both cases? Because they're positive with respect to E. So it's plus VD times X minus all of that. And how much is that there? So it's 1.5 plus 2.5. That's 4. So it'll be X minus 4.6. Did you get that? All distances are in terms of X. So X goes from there to there. So the distance from there to there is X minus 4.6. Right. Minus the UDL. Okay. Because the UDL is anti-clockwise. Now. Are you tuning in? It said there, this is a beam where the UDL does not extend to the end of the beam. Now, very important. According to Macaulay, there's a very clever person, passed on. If a beam can start anywhere, let me start again. A UDL that starts in the beam, it can start anywhere in the beam, but for Macaulay's method to work, the beam must go to, the UDL must go to the end of the beam. And I'm going to make it go to the end of the beam by doing this. So my UDL there is going from A to E. Now if I leave it like that, you can see that it's going to change the reactions. Okay? So to keep the reactions as they are, I'm going to put an upward load sitting over there to counteract that one there. So the 24 kg per meter going down will counteract the 24 kg per meter going up. Okay, so with that load sitting down and that load going up, the loading situation will remain exactly the same. But I've got to take the UDL to the end of the beam. Okay, right. I'm taking moments. So, and this is going to be minus 24. And what's the length of the UDL? It is x. It goes from A to D, so it's times x. But remember there, the UDL, it's the UDL times the length times half the length. So it's 24 times x over 2, which is 24 x squared over 2. There we go. Did you get that? Okay, it's 24 times x times half of x, which is 24 x squared over 2. Right, plus, now remember that load is from there to there. We still need to account for this piece here, plus. Why is it plus? Because that piece of load is acting clockwise with respect to E. So it's plus 24. And what's the length of that load there? It is x minus 3.1. It's x minus 3.1. But remember, that's a force. That's just the UDL times the distance. We want the UDL times the distance times half the distance. So it's 24 times x minus 3 times x minus 3 over 2. So it's going to be squared over 2. Okay, right. Did you get that? So it's 1, 2, 3. Did we get all? We still got that point load there. So it'll be minus 30 times. And how far is it from there to there? What's the distance from C to E in terms of x? It is x minus 3.1. There we go. X minus 3.1. There we go. So there's my two reactions. There's my UDL that goes from A to E. I've made it go to all the way there, but of course I got to counteract that load, that piece there. But that's 24 times its length times half its length minus that force times x minus that over there. Right. People, that's the theory of structures done really. Now we just do the mathematics. What do? We integrate twice. We integrate once, we get the slope equation. We integrate that equation, we get the deflection equation. So let's do this. So therefore the slope at x is equal to E. And of course, if I integrate that once, I get dy dx. That's going to be VB. Right, Macaulay's, keep all brackets square and don't change or remove or multiply anything out. Keep that as if it was a single variable. So it will be squared over 2 plus VD x minus 4.6 squared over 2 minus, do you agree 24 over 2 is 12? You can either leave it at or you can make it 12. So I'm going to say it's going to be 12 times x cubed over 3. That's we go. Okay. Plus 24 over 2 is 12. So it'll be 12 times, keep that a square bracket, x minus 3.1. It'll be cubed over 3. Okay. Minus 30. Times x minus 3.1 squared over 2. And of course, out of that will come a constant of integration, so it will be plus C1. Okay, you need to know your maths here. You need to know your maths here. Okay. Right, I'm gonna, let me just fix that there. Let me just make some space for myself. There we go. Let me make some space for myself. So this plus C1. Right, I need to integrate a second time, and that will give us the deflection equation. So a delta at x is equal, and of course, EI are constant, so they stay the same. And if I find the integral of dy dx, I simply get y. Okay, so I'm going to get VB times x minus 0.6. I'm keeping my square brackets there, and it will become 3, and it will become over 6 plus, and plus VD times x minus 4.6, which is now to the power 3 over 6. I'm integrating. You need to know how to integrate. Minus 12 times x to the power 4 over, that will be, it will be 12. There we go. Plus 12 times x minus 3.1. It will be to the power 4 over 12 minus 30 times x minus 3.1, x minus 3.1 cubed over 6. And that will be plus, of course, it will be C1 times x. And of course, out of that will come the second constant of integration, and we call it C2. Some people call it K2, but we call it C2. Okay, right, people? That's what's the next step in the process. We need to find C1 and C2 by using the boundary conditions. And we know that the deflection at B is 0 and at D is 0. So therefore, we're going to say that at, I can just make it a bit smaller here. B, okay, so at B, so we say at x equal to 0.6, y is equal to 0. Did you get that? At x equal to 0.6, the deflection is 0. We know that. So I'm going to put 0.6 into that equation and put 0 into there, okay? And from there, and of course, we'll be able to determine C1 and C2. Right. So what's the rules for Macaulay's? If the bracket becomes 0, if the bracket becomes negative, we set it to 0. Okay? Right, so let's see. So if that's 0 there, that will make that left side 0. So 0 is equal to, so 0.6 minus 0.6 is 0. So that's going to fall away. That's going to fall away. Let me do this here. That's going to fall away. Okay. That's going to fall away. That's going to be 0. Because no, that's nonsense. That's nonsense. That's nonsense. That's not going to fall away. Let me just change that. That's going to be 0. It falls away. That's going to be 0. It falls away. And that's going to be minus 12 times 0.6 to the power 4. 0.6 to the power 4 over 12. Okay. That's going to be 0. So that's going to fall away. That's going to be, negative. That's negative, so it's going to fall away. That's going to be negative, so it'll fall away. And that's going to be plus C1 times 0.6 plus C2. Can we solve for this? No, we can't. We can't solve for C1. We can't solve for C2 because we've got two unknowns in one equation. But let's state the equation for x at the second support there. So I'm going to say at x equal to, what's the distance there? That is 4.6. So at x equal to 4.6, the deflection there is equal to 0. There we go. Okay, so we're going to put 0 into there. We're going to put 4.6 in that equation there and set up a second equation and solve for C1 and C2 simultaneously. Right, that's going to be 0. Right, VB. So that's going to be at 4.6, that's going to be a VB. VB is 57.98, so it's 57.98 times, what's 4.6 times minus 0.6? It will be 4 to the power over 6 plus. If I put 4, that's going to be 0, so that's going to fall away. That's going to be, I want a minus, don't I? I want a minus. Here we go. That's going to be 0, so it's going to be minus 12 times 4.6 to the power 4, 4.6 to the power 4 over 12, okay, plus 12 times, what's 4.6 minus 3.1? It will be 4.6 minus 3.1, it will be 1.5, so it will be 1.5 to the power 4 over 12. Did I get it right? Yeah, I think it's correct. And minus 30 times 4.6 minus 3.1, which is 1.5 to the power 3 over 6, plus C1 times X, which is 4.6, plus C2. Right. So we've got two simultaneous equations with C1 and C2 as unknowns. Here's your high school maths. Solve it simultaneously. Stop the video, solve it simultaneously, and see what you get for C1 and C2, okay? You continue only when you get C1 and C2 exactly as to what I got, okay? Right, from there, I'll squeeze it in here, okay? From there, I found C1 to be equal to minus 39.756 and C2 to be 23.93, 23.93. Okay, I find it from there. Okay, if you assume that, you're just missing out. You go in there and you work it out, you solve simultaneously, and you see that you get C1 as 39.756. If you get 757 or 755, that's okay. Okay, right. So that means I know that now. I know that. Okay, and if I put the value for X, I can make Y the subject because that's given, and therefore I can determine the deflection at A, and then at C, and at D. Right. So at A, X is equal to 0. Lovely. X is equal to 0. Okay. So I'm gonna, so therefore E, I, Y at A. Okay. So I'm putting X equal to 0. So if it's not to 0, the bracket is set to 0. So that doesn't hold anything, neither this one, neither that one, neither this one, neither this one. Okay, that's going to be 0. So that's actually equal to C2. Okay, and C2 is equal to 23.93. Okay, alright, so therefore, what's Y equal to? I make Y the subject of the formula. So the deflection at A is equal to 23.93, and don't forget your conversion factor, okay, over EI. What's EI? I'm going back to my table there. I'm going to go back to my note quickly, and if I flick back to the question there, E is 200,000 newtons per millimeter squared, and IXX is 29 times 10 to the power 6 millimeters to the fourth. Right, so that's 200,000. If you put in 200, it's going to be 1,000 times too big, and you're going to get like a meter deflection, and it's going to be wrong. Remember, the answer must be a small number. It's a deflection. So it's 200,000 times, I'm going to check it. I think it's 29. Yes, it is 29 times 10 to the power 6. So it's 29 times 10 to the power 6 millimeters to the fourth. And if I work all that out, I get actually 4.14 millimeters. And notice there, it's actually positive. It's positive, 4 plus 4. Why is it positive? Because the beam actually is, maybe I should do it on that beam there. The beam is actually, it's actually doing this here. It's, even though it's bending down, it's doing, if I exaggerate it, it's actually doing this like so. It's doing that. So the distance from there to there is that deflection there. Okay. It's a deflection. No, it's a bend. The bend. No. Here we go. It's a deflection there. Here we go. Okay. So so even though the beam is bending downwards due to the span and the loading here, the loads are so great, it causes that end to rise, because remember it's a short piece, 0.6 meters only. That's about 4 meters there. Okay. So it rises by a distance of 4.14 millimeters above the zero line. Okay. Right. Next one. It asks us for the deflection at C. So what do? The deflection at C is where x is equal to 3.1 meters. Let's do that one. Okay. Right. At C, x is equal to 3.1 meters. There we go. 3.1 meters. Okay. So E I times y at C is equal to, right, so wherever C I see x, I put 3 in there. So that's going to be 3 minus that will be 3 minus 0.6. So it will be VB. What is VB? VB is 57.98 times 3.1 minus 0.6 is 2.5. 2.5 to the power 3 over 6 plus that's going to be 3.1 minus, so that's going to be negative, so that's set to 0. That's going to be minus 12 times 3.1 to the power 4 over 12. Okay, and of course that is going to be 1, so I'm already cancelling it out, and that's going to be 3 minus, that's going to be 0. Okay, and that's also going to be 0, so it's going to be plus C1 times x, which is 3.1. But I know C1, don't I? Silly me. Hang on. Let me fix it. I know what C1 is. Okay, we just did it at the top there. Thank you. Sorry about that. So it's plus C1 times x. C1 is a minus 39.756. 39.756 times x, which is 3.1. Plus C2, which is 23.983. 20. Oh man. Time to write smaller, need 23.983. Okay, there we go. Right. And you work all that out, and you should get an answer of minus 40.623. Okay. Now I'm going to make that the subject of the formula. So therefore, y at C is equal to all of that, 40.623, multiplied by our conversion factor of 10 to the power 12, and I divide it over EI. What's E is 200,000 newtons per millimeter squared. What's I in this case is 29 times 10 to the power 6 millimeters to the fourth. And if I work all that out, I get a negative value of exactly 7 millimeters. And why is it negative? Because it's dropping that amount. Okay, if I draw it on there to be that distance from there to there. It's the amount the beam drops below there to that point there. And it's minus because it's dropping below the zero line. Okay, people, so that there is the deflection at point C. The question this is, find the reflection at E there. Okay, I'm expecting it's going to be also positive because the beam is going to bend down, but it's going to end up there. Right, so I'll do that quickly. I think maybe you can do that on yourselves. To find the deflection at E, what's the value of x? X is equal to 5.6. So at E, x is equal to 5.6. Put x equal to 5.6 in all of that, and you make y the subject. You know what E is, you know what R is, and from that you should get, let me write it here somewhere, you should get deflection at E is equal to 0.20 millimeters. Okay, do it and see you get that there. The answer is positive. That means the beam does rise ever so slightly above the zero line. So that's a deflection there at E. Okay, and that is the whole question done, I think. It doesn't want you to find the slope anywhere. It says calculate deflection AC and E, given E that and R that. Okay, so people, that's the end of lesson 2. Work through all of that. If I continue, if I go back up to numbers 2 and 3, I've done number 1, do number 2, do number 3, do all of them, right? Notice here by number 4, the cantilever, the UDL goes to the end, so you don't make it go to the end, it's already going to the end of UDL. Okay, so you just take moments about E, with origin starting at A and going to the right as always. Okay, we just done this one. Number 6. Oh, okay, number 6. Yeah, when you do this one here, okay, that UDL goes to the end. You don't do anything about it. This one here, the UDL, if I just write it in here, let me see. See if I can write on here. This is very temperamental. Right. But number 6, is it number 6? Yes, number 6, okay? When you take moments about this one here, this UDL, because it doesn't go to the end, you make it go to the end like so, okay? And then you add another upward UDL starting over there, going there, okay? So the moment due to this UDL is minus 50 times x over 2, yeah? Taking moments by G. Minus, because it's anti-clockwise with respect to G, so it's minus 50 times x over 2, okay? And then that one you also treat minus 60 times x minus, okay? And of course, don't forget this UDL is going clockwise, so it'll be plus 50 times x minus, the length of it is x, what will be the, from there to there? That will be x minus 2.2 times x minus 2.2 squared over 2. Okay, so don't forget that UDL you need to take to the end and add an upper UDL to balance it out so that the loading situation stays the same. Otherwise you change the loading. Okay, number 7. Oh, number 7 getting a bit harder. This UDL you need to take to the end like so, and then add one there. This UDL you need to take to the end too, and you need to add one there as well to balance it out. And notice it gets more complicated, but it's doable. Okay, work through all of them. I will put the answers for each of those, and for each of those deflections on Blackboard, I'll put the answers for the deflection and the slope. And I will also do another one. I'll do a cantilever where I need to work at the deflection at the far end. Okay. Okay, people, I shall see you in the next lesson for the cantilever deflection.